What is waiting for us in the absolute dark past Pluto? Our solar system does not end with the last planet. It stretches into a profound and hidden frontier, a place of ancient ice and deep cold known as the Oort Cloud. This is the inner Oort Cloud, a vast spherical reservoir of trillions of frozen objects. It is a cosmic vault holding secrets from the very birth of our planetary neighborhood, and it may contain the raw materials that will power our future among the stars. By the end of this exploration, you will understand how this distant cloud shapes everything from the comets in our sky to the potential for life itself. We will see how its strange inhabitants hint at undiscovered worlds, and how it acts as a gravitational shield and sometimes a threat for our tiny blue planet. What do you believe is the most important thing we could learn from the edge of our own solar system? To truly grasp its nature, we must first place it on the map. Our solar system is not just a flat disk of planets. It is layered like an onion with rings and shells of debris extending far into the void. Closest to us past Neptune is the Kuiper Belt, a relatively flat donut of icy bodies like Pluto. But beyond that, the structure changes. Far, far beyond lies the classic Oort Cloud, a gigantic spherical shell of frozen objects so distant that the sun is just a bright star. The Oort Cloud sits squarely in the vast and mysterious gap between these two known regions. It is named for the astronomer Jack G. Hills, who in the early 1980s used mathematical models to suggest that a dense inner region of this cloud must exist. His work was not about finding new objects with a telescope, but about solving a puzzle. Where were all the long-period comets, those ancient wanderers that take thousands or even millions of years to orbit the sun, actually coming from? The outer Oort Cloud was too diffuse, its objects too loosely bound. Hills calculated that a denser, closer reservoir was needed to nudge enough comets inward toward us. This reservoir is what we now call the Oort Cloud or the inner Oort Cloud. Think of it not as a perfect sphere, but as a thick, fuzzy torus, a cosmic inner tube beginning around 1,000 times farther from the sun than Earth is, and stretching out to an almost unimaginable 20,000 times that distance. At its inner edge, you are still a trillion miles from home. This immense distance is why we have never directly seen an object residing there. Its members are too dark, too cold, and too far away to reflect any meaningful light back to our telescopes. Yet we know it must be there because of the comets. This cloud acts as a deep freeze storage unit, preserving primordial material from the solar system's infancy. Every so often, the gentle gravitational nudge from a passing star or the collective pull of the galaxy itself dislodges one of these frozen relics. It begins a slow, multi-million-year fall sunward, warming up, growing a glorious tail, and becoming a long-period comet in our night sky. So, while the Kuiper Belt is our local icy neighborhood, and the outer Oort Cloud is a distant, tenuous halo, the Oort Cloud is the active inner sanctum, the bustling warehouse where most of these spectacular celestial visitors begin their epic journeys. The proof of this hidden cloud is written in the paths of comets across our sky. Think of a long-period comet like the magnificent Hale-Bopp that graced our nights in 1997. Its orbit was not a neat ellipse within the planetary zone, but a wildly stretched arc that took it thousands of times farther from the sun than Earth. Where did such a journey begin? Astronomers can trace these orbital paths backward like cosmic detectives following a trail of celestial breadcrumbs. The origin point for so many of these comets is not the unimaginably distant outer Oort Cloud, but a region much closer, though still profoundly far. The math reveals a concentration, a gravitational well from which these icy wanderers are being gently plucked. This is the primary evidence for the Oort Cloud, a statistical signature of a dense inner reservoir. But the detective work does not stop there. scientists run sophisticated computer simulations of our solar system's place in the galaxy. They model the gentle tugs of passing stars over billions of years. These simulations show that the sparse outer cloud alone could not supply the number of comets we see. A denser inner region, however, fits the data perfectly. Its objects are close enough to be disturbed by these stellar flybys, yet still so far out that they remain in a deep freeze for eons. The most tantalizing clues, however, come from a handful of strange, frozen worlds we have actually spotted. These are objects like Sedna, discovered in 2003, and another named 2012 VP113. They are called sednoids, and their orbits are bizarre. They never come close to the giant planets, yet they also never venture out to where the classic Oort Cloud begins. They are stuck in a gravitational no-man's land, looping on elongated paths entirely within the proposed zone of the Hills Cloud. Their existence is like finding a few strange fish in a vast, dark ocean, telling us that an entire hidden ecosystem must be there. They are not proof of the cloud itself, but they are powerful evidence of its gravitational influence, like ripples on water pointing to a submerged giant. So we know the Hills Cloud is there not because we can see it, but because we can see its effects, the subtle fingerprints it leaves on everything that comes from the deep dark. The story of the Hills Cloud is a story of cosmic chaos and exile. To understand its ancient origins, we must travel back in time to the solar system's violent birth over 4.6 billion years ago. Our sun ignited within a swirling, flattened disk of gas and dust, the protoplanetary disk. In the hot inner regions, rocky planets like Earth began to form. But farther out, in the deep cold beyond the frost line, vast amounts of ice and frozen gases coalesced into the cores of the giant planets, Jupiter and Saturn. As these behemoths grew, their immense gravitational influence began to act like a cosmic wrecking ball. They stirred the outer solar system into a frenzy, scattering countless icy planetesimals, the leftover building blocks of planets, in every direction. Many were flung inward, bombarding the inner planets in an era we call the Late Heavy Bombardment. But many others were hurled outward on trajectories that should have sent them flying into interstellar space forever. Yet they did not all escape. Here is the crucial part of the story. The combined gravity of the infant sun and the galaxy itself created a boundary, a sort of gravitational shoreline. Some of these exiled ice worlds were thrown with just enough force to reach the edge of the sun's influence, but not enough to break free completely. They sailed out to the farthest reaches of its gravitational grasp, and there they became trapped. They found a stable, if incredibly distant, orbit in what would become the Oort Cloud. The densest concentration of these stranded relics, the ones that got a strong kick but not the strongest, settled into the region we now call the Hills Cloud. This makes it a fossilized remnant of that primordial disk. While the inner planets were melted and reformed, and the asteroid belt was pummeled and reshaped, the objects in the Hills Cloud have been in a state of deep freeze since the very beginning. They have never felt significant heat from the sun. They have never been altered by planetary geology. They are pristine time capsules, preserving the original chemical and isotopic ingredients of our solar system's construction in a cosmic freezer set to just a few degrees above absolute zero. When we study a comet that originates from this cloud, we are not just looking at a pretty light in the sky. We are analyzing a sample of the raw material from which our entire neighborhood was built, delivered to our doorstep from a vault at the edge of everything. This cosmic vault of primordial ice is so vast it defies everyday understanding. To begin mapping its scale, picture our entire solar system as we know it, with Neptune orbiting at the edge. Now multiply that distance by 1,000. That is merely the inner boundary of the Hills Cloud, the starting line of this immense frontier. From that point, the cloud stretches outward for tens of thousands of astronomical units, creating a spherical shell of staggering emptiness and occasional frozen points of matter. If you could shrink the sun to the size of a grain of sand here on Earth, the inner edge of this cloud would be over half a mile away, and its outer reaches would extend to the other side of a large city. Within this incomprehensible volume, the population is estimated to be in the trillions. We are not talking about just small, dirty snowballs, though countless of those exist. This region likely holds dwarf planets larger than Pluto, and perhaps even full-sized rogue planets that were violently ejected from the inner solar system during its chaotic youth, or even captured from other passing stars. These are dark, cold monarchs wandering a perpetual night, so distant that our sun provides less light than a full moon does for us. This is why we have never directly imaged a confirmed resident of the Hills cloud. The technological challenge is immense. These objects do not generate their own light, and the sunlight that reaches them is vanishingly faint, reflecting back a signal so weak our current telescopes simply cannot pick it out from the background noise of the universe. It is like trying to spot a lump of coal blacker than asphalt floating in the deep ocean at midnight using a single candle held on a distant shore. This fundamental darkness is the great barrier to our exploration, a silent curtain drawn across the deepest reaches of our own home system. Yet, the drive to lift that curtain is fueling the next generation of astronomical ambition. These trillions of frozen relics are not simply parked in eternal silence. The Hills cloud acts as a dynamic factory, the primary production line for the most spectacular visitors to our inner solar system, the long-period comets. While its vast distance provides stability, it is not a perfect shield. The gentle, relentless forces of the galaxy itself are always at work, nudging these dormant ice worlds onto new paths. The primary mechanism is the gravitational pull of stars that pass relatively close to our solar system. Every few million years, another star wanders through the outer reaches of the Oort Cloud, its gravity acting like a subtle pluck on a cosmic harp string. This stellar flyby can perturb the orbit of a Hills cloud object just enough to send it tumbling inward. Similarly, our solar system, as it orbits the galaxy, occasionally passes through dense patches of interstellar gas and dust known as giant molecular clouds. Their collective mass can also exert a tidal force, shaking loose new cometary candidates. And always there is the background pull of the Milky Way itself, the galactic tide, which constantly stretches and squeezes the distant cloud like an invisible hand. When one of these distant objects receives that fateful gravitational kick, its multi-million-year journey begins. For millennia, it falls silently sunward, a dark speck against a darker void. But as it crosses into the realm of the giant planets, its destiny transforms. The sun's warmth, still feeble at such distances, starts to vaporize the frozen gases on its surface, primarily water ice, carbon dioxide, and carbon monoxide. This process accelerates dramatically as the object, now officially a comet, enters the inner solar system. The ices don't just melt, they sublimate, turning directly from solid to gas, erupting from the nucleus and dragging dust grains with them. This creates the comet's magnificent coma, the fuzzy atmosphere that can grow larger than a planet, and its iconic tails. The dust tail, glowing by reflected sunlight, curves gently behind it. The ion tail, made of charged gas molecules pushed directly away from the sun by the solar wind, points like a ghostly blue finger straight out into space. This breathtaking transformation directly links the abstract, invisible reservoir at the solar system's edge to the awe-inspiring phenomena in our night sky. Every long-period comet that graces our heavens, from the historical Great Comet of 1882 to the more recent McNaught Comet of 2007, is likely a messenger from the Hills cloud. It is a piece of primordial solar system material, preserved in a deep freeze for billions of years, now putting on a final, fiery performance before its ices are spent or its orbit is altered by a planetary encounter. So when you look up at a comet with a tail stretching across the stars, you are not just seeing a beautiful accident. You are witnessing the end result of a celestial chain reaction that began with a stellar nudge a trillion miles away in the silent, dark factory at the border of our sun's dominion. The discovery of Sedna in 2003 was a profound shock to our understanding of the solar system's architecture. Here was a world roughly half the size of Pluto, yet its orbit was unlike anything seen before. Sedna takes approximately 11,400 years to complete one lonely loop around the Sun. At its closest approach, it is still far beyond Neptune, utterly detached from the gravitational influence of the giant planets. At its farthest, it retreats to a staggering distance, yet it does not reach out to where the classical Oort Cloud is thought to begin. Sedna and the handful of similar objects found since are prisoners of a gravitational niche. They are trapped in a narrow band, forever looping in a no-man's land between the Kuiper Belt and the outer Oort Cloud. This is precisely the domain of the theorized Hills Cloud. These objects, now called sednoids, are not mere curiosities. They are the first concrete evidence, the first physical messengers, telling us that this distant reservoir is not empty. Their very existence confirms that a vast population of objects must occupy that orbital space, and we are only seeing the very largest and brightest of them by sheer luck. Their detached orbits are a frozen record of ancient violence. An object does not get placed on such a lonely, elongated path by accident. It requires a powerful, singular gravitational kick. The leading theory is that Sedna was flung outward during the solar system's chaotic early days, perhaps by a close encounter with Neptune or another giant planet when their orbits were still shifting. But instead of being ejected entirely, it was captured by the gentle, persistent pull of the galactic tide, the combined gravity of the Milky Way itself, which acts as a weak but enormous background force. This placed it in a stable, if incredibly distant, orbit within the Hills Cloud. The story gets even more intriguing when we look at the orbits of several of these extreme objects together. Astronomers have noticed that a cluster of them share a peculiar orbital alignment, as if something massive is herding them, keeping their closest approaches to the Sun clustered on one side of the solar system. This strange pattern is one of the key pieces of evidence pointing to the possible existence of Planet 9, a hypothetical world several times the mass of Earth, orbiting far out in the darkness. Whether it is Planet 9, the collective gravity of the Hills Cloud itself, or the echoes of a stellar flyby billions of years ago, the sednoids are telling us that the gravitational landscape at the edge of our system is complex and sculpted by unseen forces. Sedna itself is a haunting preview of what the inner Oort Cloud may hold, a world likely covered in deep red organic compounds and water ice, colder than any place we have ever directly observed, bathing in a perpetual twilight where the Sun is little more than an intensely bright star. It is a fossil from the dawn of our solar system, and its lonely journey hints at the multitudes of similar, and perhaps even stranger, worlds waiting silently in the vast dark. The strange, herded orbits of Sedna and its kin point to a profound mystery. If these distant objects are not simply random, their peculiar alignment could be the signature of a hidden architect, a massive world we have yet to see. This is the Planet 9 hypothesis, a bold idea suggesting a Neptune-sized planet, 5 to 10 times the mass of Earth, is silently orbiting far beyond Pluto. Its gravitational hand would be gently shepherding these smaller bodies, explaining why their closest approaches to the Sun all cluster in one particular region of the sky. The planet itself would follow an immensely elongated orbit, swinging from perhaps 300 times Earth's distance from the Sun out to over 600 times that distance or more. This path would take it right through the proposed territory of the inner Oort Cloud, making it not just a planet, but perhaps the dominant resident of that shadowy realm. For such a world to exist, it must have formed in the early solar system alongside the other giants. The prevailing theory is that it was born closer to the Sun, but suffered a gravitational slingshot from Jupiter or Saturn, hurling it onto a wild, eccentric path that stabilized in the distant freeze. It would be a dark, cold giant, reflecting virtually no sunlight, which is precisely why we have not found it yet. The search for Planet 9 is a monumental game of celestial detective work. Astronomers are not simply pointing telescopes at random patches of dark sky and hoping. They use the observed orbits of the sednoids and other extreme objects to calculate the possible path of the unseen perturbing mass. This creates a predicted orbit, a vast, narrow highway in the sky where the planet must be traveling. Powerful telescopes, like the Subaru telescope in Hawaii, then methodically scan these predicted corridors, taking deep, sensitive images to detect the faintest speck of motion against the fixed background of stars. They are looking for a single, slow-moving dot in an ocean of darkness. Finding it would be one of the greatest astronomical discoveries in a century, reshaping our solar system's family portrait. It would confirm that our planetary system extends far beyond the known 8, and that the Hills Cloud is not just a repository of icy debris, but a dynamic zone capable of harboring major worlds. It would also provide a natural explanation for other orbital oddities in the distant solar system, tying together many loose ends with a single, elegant gravitational solution. The hunt continues, a testament to the fact that even in our own cosmic backyard, the greatest giants may still be hiding in plain darkness. The search for hidden giants like Planet 9 reveals a solar system far more porous than we once believed. Our cosmic neighborhood is not a sealed vault, but an open crossroads visited by wanderers from other stars. In 2017, astronomers detected an object unlike any other, a dark, reddish visitor named Oumuamua, tumbling past the sun at incredible speed. Its trajectory and velocity made one thing indisputable: it was not from here. It was our first confirmed interstellar interloper, a piece of another planetary system passing through ours. Then, in 2019, we spotted a second comet Borisov, a more familiar-looking icy body, but with the same telltale interstellar origin. These were not messengers from our own Oort Cloud, but travelers from the vast galactic sea. Their fleeting visits raise a profound question about the nature of our own distant frontier. Could the Hills Cloud, that vast spherical shell at the edge of our sun's influence, act as a cosmic fishing net, capturing such rogue objects as they drift through the galaxy? The physics is compelling. An interstellar object passing too close to our solar system would typically be deflected by the sun's gravity and slingshot back out into the void on a hyperbolic path. But if its approach is just right, slow enough and aimed precisely, the combined gravity of the sun and the outer planets could slow it down just enough to trap it in a bound orbit. The most likely place for this capture to occur is in the distant, chaotic gravitational environment of the Oort Cloud, with its immense volume and relatively weak solar hold. The inner Hills Cloud, being denser, might be an especially effective trap. This leads to a startling possibility. Some of the trillions of objects we believe reside in our own Hills Cloud may not be native to our solar system at all. They could be cosmic captives, ancient wanderers snared billions of years ago when our sun was younger and moving through a denser stellar neighborhood. These frozen prisoners would be mixed in with our own exiled planetary building blocks, indistinguishable from a distance. Studying the population and dynamics of the Hills Cloud, therefore, is not just about understanding our own origins. It becomes an exercise in cosmic archaeology, sifting through the solar system's attic to find artifacts from other stars. Every long-period comet that arrives from that distant cloud could, in theory, be one of these captives, its chemical composition telling a story not of our sun's birth, but of a different stellar nursery entirely. The discovery of Oumuamua and Borisov gives us a critical data point. By observing how many such visitors pass through, we can begin to estimate how many might have been captured over the eons. Current estimates suggest that for every star like our Sun, there could be trillions of these free-floating planetary remnants drifting between the stars. If that is true, then our Oort Cloud and the hills cloud within it might be a rich museum of stolen relics, a silent library of other worlds' histories, all held in the deep freeze at the very edge of our light. This silent library of frozen history may hold the keys to our future, but reaching it is the greatest engineering challenge humanity has ever conceived. A direct mission to the hills cloud is not a journey measured in years, but in human lifetimes. Even with our fastest existing propulsion, a probe like Voyager would take tens of thousands of years to reach the inner edge. To make this voyage in a meaningful time frame, we must leap beyond chemical rockets and embrace technologies that sound like science fiction, but are grounded in real physics. One leading contender is nuclear thermal propulsion. Instead of burning fuel, this system uses a nuclear reactor to superheat liquid hydrogen, blasting it out a nozzle at incredible speeds. This could cut travel time to the outer solar system by more than half, but for the hills cloud we need more. We need sustained acceleration over decades. This is where concepts like solar sails and laser sails enter the picture. Imagine a spacecraft with a sail thinner than a human hair, kilometers wide, catching the gentle but constant push of sunlight itself. In the inner solar system, this provides a slow but fuel-free acceleration. For a true interstellar sprint, we look to break through concepts like Starshot, which proposes using a powerful ground-based laser array to blast a tiny, gram-scale sail with a concentrated beam of light. This could theoretically accelerate a nanocraft to a significant fraction of light speed, reaching the hills cloud in a matter of decades rather than millennia. Each of these ideas shatters our conventional thinking about space travel, turning a voyage to the edge from an impossible dream into a staggering but conceivable engineering project. The spacecraft that embarks on this century-long odyssey must be a marvel of autonomy and endurance. Power is the first monumental hurdle. Solar panels are useless so far from the sun, where sunlight is a faint memory. The only reliable source for such a mission is nuclear. Not just radioisotope thermoelectric generators like those on the Voyagers or Perseverance, but potentially full-scale fission reactors that could provide kilowatts of power for propulsion, instruments, and communication for 100 years. Communication presents another profound challenge. A signal from the inner hills cloud would take weeks to travel one way, and its strength would be vanishingly weak by the time it reached Earth. We would need a network of enormous radio dishes across the solar system, perhaps on the far side of Mars or in the asteroids, acting as signal boosters in a deep space internet. But the most profound shift is in spacecraft intelligence. With round-trip communication delays measured in months, the probe cannot wait for instructions from Earth. It must be governed by a sophisticated, resilient artificial intelligence, capable of navigating unknown hazards, prioritizing scientific targets, and repairing its own systems. This AI would be the embodiment of human curiosity, making real-time discoveries in a realm we cannot see, and deciding for itself what is worth sending back across the unimaginable gulf. So what would such a mission actually look like? One compelling profile is not a single heroic vessel but a swarm. Imagine launching a mothership on a nuclear-powered trajectory toward the general vicinity of the hills cloud. Years into its cruise, it releases a cloud of hundreds of tiny, chip-sized probes, each equipped with basic sensors and its own microscopic light sail. The mothership then activates a powerful onboard laser, bathing the entire swarm in a focused beam, pushing this fleet of explorers outward like dandelion seeds on a photon wind. These nanocraft would fan out, creating a vast sensor net. As they drifted through the cloud over decades, their simple instruments could measure the density of microscopic dust, sample the faint molecular environment, and even detect the subtle gravitational tug of hidden dwarf planets. They would not send back beautiful pictures but torrents of raw data, bits and bytes that would, over a century, assemble into the first true map of this invisible frontier. Another concept involves a larger, more traditional orbiter designed to rendezvous with a specific sednoid like Sedna itself. After a 50-year journey, it would enter orbit around this frozen fossil, mapping its surface in detail, analyzing its composition with spectrometers, and perhaps even deploying a lander to taste its primordial ice. The data returned would tell us not just about one strange world, but serve as a representative sample for the entire hidden population. These mission profiles are blueprints for patience, requiring a societal commitment that spans generations. The scientists who design them would never see the results. The engineers who build them would hand the project off to their students, and then to their students' students. A mission to the Hills Cloud is a conversation with the future, a message in a bottle we launch today for our great-grandchildren to open, containing nothing less than a revolutionary portrait of our home in the cosmos, and perhaps the first clues to what lies beyond it. That deep space gas station is already built and its tanks are full. The Hills Cloud is not merely a museum of the past, but a cosmic warehouse for our future, holding the fundamental ingredients for life and industry in staggering abundance. Each of its trillions of frozen objects is a potential resource depot, a flying mountain of critical materials. The most vital of these is water ice. We often think of water as the essence of life, and it is, but in space it is also the essence of propulsion. Through a process called electrolysis, water can be split into its component parts, hydrogen and oxygen, the most powerful chemical rocket fuel combination that exists. Imagine a network of robotic harvesters stationed in the inner Oort Cloud, intercepting small cometary bodies. They would not land in the traditional sense, but latch onto these dark, tumbling mountains. Using focused sunlight or compact nuclear reactors for heat, they would drill into the ice, extracting and processing it on site. The purified water could be stored or immediately cracked into liquid hydrogen and liquid oxygen, creating fuel depots in the deepest reaches of our solar system. This transforms the entire paradigm of exploration. A spacecraft launched from Earth would no longer need to carry all the fuel for its entire mission. It could travel on a lean, efficient trajectory to the edge of the system, refuel at a Hills Cloud depot, and then have a full tank to explore the outer planets, their moons, or even accelerate toward another star. The economics of spaceflight are inverted as the most distant region becomes the most practical place to fuel up. Water is just the beginning. These icy bodies are also rich in frozen volatiles, gases like methane, ammonia, and carbon dioxide, all trapped since the solar system's birth. Methane can be used as another rocket fuel, often easier to store long-term than hydrogen. Ammonia is a fantastic source of nitrogen, a crucial element for fertilizing soil in closed-loop life support systems for space habitats. Carbon dioxide is the raw material for producing breathable oxygen and for growing plants. A single, modestly sized comet from the Hills Cloud could contain more of these life-giving volatiles than all the reserves ever mined on Earth. Harvesting them would mean we are not just carrying our environment with us in fragile bubbles, but learning to live off the extraterrestrial land, a concept known as in situ resource utilization pushed to its absolute limit. This turns the desolate outer solar system from a forbidding desert into a frontier ripe for settlement. A habitat orbiting Saturn or mining the asteroids of the Kuiper Belt could order regular shipments of water and air from the Hills Cloud supply depots, delivered by autonomous tanker craft on predictable orbits. The cloud becomes the agricultural and industrial heartland for an entire outer system civilization, its resources flowing inward on celestial trade routes. Perhaps the most profound resource, however, is not for machinery but for life itself. Locked within that ancient ice are complex organic molecules, the carbon-based building blocks from which all life as we know it is constructed. We have detected molecules like formaldehyde, hydrogen cyanide, and even amino acid precursors in comets from the closer Kuiper Belt. The pristine objects of the Hills Cloud, untouched for billions of years, likely contain an even richer and more diverse array of these prebiotic compounds. For future scientists and bioengineers living in space, these would not just be curiosities but a literal feedstock. They could be extracted and studied to understand the origins of life, or potentially used in advanced synthesis to create medicines, materials, or nutrients that are difficult to produce from scratch. The cloud offers a cosmic chemistry set, providing the raw organic ingredients that could help a disconnected human society remain healthy, adaptable, and self-sufficient far from Earth. This vision transforms the Hills Cloud from a distant, passive reservoir into the central utility hub for a solar system-wide civilization. Its endless night and unimaginable cold become assets, the perfect conditions for preserving these volatile treasures. The same gravitational nudges that send comets toward the Sun today could, in a future of advanced celestial engineering, be used to gently guide resource-rich asteroids into stable orbits where processing plants await. The silent frontier at the edge of our Sun's light would hum with quiet industry, its bounty enabling humanity to become a truly interstellar species, forever changing our relationship with the dark. But this cosmic warehouse holds a darker potential, a dormant threat in the deep freeze. The same gentle gravitational nudges that send us occasional spectacular comets could, under the wrong cosmic alignment, unleash a storm. Astronomers call it a comet shower. It begins with a rare and close encounter, a star passing through the outer Oort Cloud. Not a distant flyby, but a true trespasser coming within a light year or less of our Sun. Its gravity would not just pluck a few icy relics from the Hills Cloud. It would violently shake the entire reservoir like a hand stirring a snow globe. In a relatively short astronomical time frame, this could dislodge not just dozens but millions of objects, sending a wave of comets cascading inward. The inner solar system would face a bombardment lasting hundreds of thousands of years, dramatically increasing the chance of a catastrophic impact with Earth. Our planet's history is written with the scars of such events. The most famous is the Chicxulub impactor, the asteroid or comet that struck 66 million years ago, ending the reign of the dinosaurs. While its exact origin is debated, some compelling models suggest it could have been part of a larger comet shower triggered by just such a stellar disturbance. The geological record shows other periods of heightened impact activity, and correlating these with times when our Sun likely passed closer to other stars is an active area of detective work. This transforms our view of the Hills Cloud from a passive reservoir to a loaded gun, with a galactic passerby potentially pulling the trigger. The timeline is both terrifying and reassuring. Such close stellar encounters are rare, perhaps happening only once every few 100 million years. We are likely living in a relatively quiet interval. Yet, the threat is real enough that understanding the dynamics of our distant cloud is no longer just about curiosity, it is about survival. This is where future monitoring of the Hills Cloud becomes a critical pillar of planetary defense. We cannot see the objects directly, but next-generation sky surveys like the Vera C. Rubin Observatory will map the entire visible sky with unprecedented depth and frequency. By cataloging the influx of new long-period comets from the cloud, we could detect the early signs of a shower decades or even centuries before the peak of the bombardment. An anomalous surge in these deep space visitors would be a bright red warning light flashing from the edge of the solar system. That lead time is everything. It would allow humanity to focus our defensive efforts, to track the most dangerous incoming trajectories with precision, and to develop and deploy deflection technologies, whether kinetic impactors, gravity tractors, or focused energy beams. The silent sentinels at the solar system's edge, once a source of mystery, could become our earliest warning system, their ancient ice whispering of dangers still millennia away but written in the paths of the first messengers. Our own distant cloud offers more than just a map of our past. It provides a universal blueprint. The principles we have uncovered here must apply to other stars as well. Every sun like ours, born from a similar nebula, should have cast off its own icy debris into a spherical halo, creating its own Oort Cloud. The search for these distant reservoirs has already begun, pushing our telescopes to their absolute limits. We cannot see them directly, but we can detect their faint collective heat. Powerful infrared observatories like the James Webb Space Telescope scan nearby stars for an excess of infrared light, a telltale glow that suggests a vast, cool shell of icy material surrounds them, radiating the absorbed warmth of its star back into space as a subtle thermal signature. Another ingenious method uses the gravity of the cloud itself. When a star with a dense Oort cloud passes in front of a more distant star, its gravitational field, amplified by all that hidden mass, can act as a lens. It briefly bends and magnifies the background starlight in a detectable event called microlensing. These fleeting cosmic alignments can betray the presence of a massive, unseen halo of objects. Finding these exoclouds transforms our understanding of planetary systems. A robust Oort cloud is not a mere decoration, it is a sign of a dynamic and violent history. Its existence tells us that the star system likely formed giant planets that did the heavy work of flinging material outward, sculpting the architecture we see today. More importantly, it suggests the system possesses a persistent delivery mechanism for the ingredients of life. Just as our Hills cloud occasionally sends comets inward, an Oort cloud would rain water and probiotic organic compounds down onto any rocky inner planets. This continuous, gentle fertilization could be a critical factor in starting and sustaining biology. It means the galactic habitable zone, the region of a galaxy where conditions are right for life, may not just be about a star's stability or the presence of planets. It may also depend on whether that star system successfully built and maintained a distant icy reservoir. A system without a substantial Oort cloud might have inner worlds that are dry and barren, having lost their volatile elements early on. Our solar system, with its active Hills cloud, might therefore represent a privileged class of stellar environment. We are not just a rocky planet at the right distance from our Sun. We are part of an intricate, multi-layered life support system that stretches to the farthest gravitational reach of our star. The comets that brought water to early Earth, and perhaps even the complex molecules that sparked life, were shipments from this distant warehouse. When we look for life elsewhere, we are not just looking for another Earth. We are searching for another solar system with its own healthy, functioning Oort cloud, a silent partner in the cosmic drama of habitability. Our cloud is the only one we can study in detail, making it the essential template for understanding how the deepest cold of space might nurture the warmth of life. The clock that governs the Hills cloud is not one we can hear ticking. It is a galactic metronome beating with a rhythm so slow it defies human perception. Within this distant reservoir, time is measured not in seasons or centuries, but in orbital periods that span tens of thousands, even millions of years. An object like Sedna completes a single, lonely lap around the Sun every 11,400 years. Its last closest approach occurred around the end of the last ice age, when woolly mammoths still walked the Earth. Its next return will occur in a future so distant, our entire recorded history from the pyramids to the present day is merely a brief interlude in its endless cycle. Other denizens of the cloud have orbits stretching into the millions of years, their journeys so elongated that the Sun's gravitational hold is but a whisper at the farthest point. To exist in the Hills cloud is to experience time as geology does, where change is measured in the drift of continents and the slow cooling of stars. This immense timescale is shaped by forces far greater than our Sun. The primary clockmaker is the Milky Way galaxy itself, As our solar system orbits the galactic center, it bobs up and down through the plane of the disk, completing a cycle roughly every 60 million years. This motion subjects the distant Oort Cloud to a persistent, rhythmic pull known as the galactic tide. Think of it as the gentle, cosmic equivalent of the ocean's tide, but one that stretches and squeezes the cloud over tens of millions of years, slowly stirring its frozen inhabitants. This tidal force is what ultimately nudges comets loose from their frozen slumber, setting them on their long fall sunward. A comet's multi-million-year journey from the cloud to our skies is not a frantic sprint, but a stately, inevitable procession governed by this galactic rhythm. It means the beautiful comet you might see tonight was likely set in motion by a galactic tide that peaked when dinosaurs ruled the planet. This perspective forces a profound shift in how we see our place in the cosmos. Human civilization, with all its tumult and triumph, occupies less than a heartbeat on this galactic clock. Our written history is a flicker against a backdrop of deep time where the Hills Cloud acts as a constant, patient witness. It frames our solar system not as a static snapshot, but as a dynamic entity with a long-term future still being written. The cloud's slow dance reminds us that the processes that built our home, and that will one day change it, operate on a stage far vaster than our own. It encourages a humbling and expansive view, where we are both fleeting observers and the first generation capable of understanding the immense, silent clockwork ticking at the edge of our light. This silent, galactic clockwork may hold more than just frozen water and rock. It could preserve the very spark of life itself. The ancient ices of the Hills Cloud are central to one of the most profound and debated ideas in science, panspermia. This is the theory that life, or its fundamental building blocks, can travel between planets and even between star systems, hitching rides on asteroids, comets, or cosmic dust. Our distant cloud offers a compelling mechanism for this cosmic transfer. Imagine a scenario in the solar system's violent youth. A massive asteroid slams into the young, wet Earth, or perhaps into a warmer, wetter Mars. The impact is cataclysmic, blasting plumes of vaporized rock and water high into space. Within that ejected material could be hardy microorganisms, deep-dwelling bacteria that survived the initial shock, encased in protective shells of rock. Most of this debris would fall back or be sterilized by radiation, but a tiny fraction could receive just the right trajectory, a gravitational kick from Jupiter that flings it not just out of the planetary zone, but all the way to the distant gravitational embrace of the Oort Cloud. There, in the permanent deep freeze a few degrees above absolute zero, these microbial stowaways enter a state of suspended animation. Radiation is minimal, chemical reactions are virtually halted, and time, for all practical purposes, stops. They become biological time capsules preserved for billions of years within their rocky tombs, drifting in the silent dark. The Hills Cloud, in this view, is not just a warehouse of raw materials, but a cosmic archive, a natural freezer storing snapshots of early planetary biology from a time when life on Earth was just beginning its experiment. This raises a staggering possibility. Could a comet from our own cloud, dislodged by a stellar nudge millions of years from now, eventually fall back inward and deliver these ancient, dormant Earth microbes to another world, like a future Europa or Enceladus, reseeding life from our own past in a different ocean? The cloud becomes a biological backup drive for the solar system, but the flow of material could also run the other way. The classic form of panspermia suggests life's ingredients arrived here from elsewhere. Comets from the Hills Cloud are perfect delivery vehicles. We know they carry water, complex organic molecules, and even amino acids. When they bombarded the early Earth during the late heavy bombardment period, they were not just destructive forces, they were supply ships. They could have delivered the vast oceans that fill our basins and the essential probiotic chemicals that, in the warm, shallow pools of our young planet, assembled into the first self-replicating molecules. The cloud, therefore, acts as both a reservoir and a distributor. It gathers the primordial soup ingredients manufactured in interstellar space and in the outer solar system, freezes them for safekeeping, and then, on a slow galactic timetable, dispatches them to inner worlds like ours. This transforms our view of life's origins from a lonely planetary event into a potentially system-wide or even galaxy-wide process. If our solar system's cloud can act this way, then so can every other star's Oort Cloud. The galaxy becomes crisscrossed with icy messengers, trading volatile compounds and perhaps biological precursors between stellar families over billions of years. The deep freeze at the edge of every sun's influence becomes the universal cold chain, ensuring these fragile ingredients survive their epic journeys between the stars. While the idea of fully formed microbes surviving an interstellar journey is hotly debated, the simpler transfer of life's building blocks is widely accepted. The Hills Cloud stands as the critical way station in that grand cosmic logistics network, a silent curator of the materials that make living worlds possible. The slow dance of these frozen relics could one day become the foundation for our eyes and ears across the galaxy. Among the most ambitious ideas born from understanding the Hills Cloud is a concept that turns our entire solar system into a scientific instrument. It begins with a prediction from Einstein's theory of general relativity that massive objects like our Sun bend the fabric of space-time, acting as a gravitational lens. This bending can focus light from a distant object just like a glass lens. For a star, this focus is not a single point, but a long, narrow line stretching directly away from it into space. The sweet spot where the light from a distant star or exoplanet is brought into a perfect ring of focus begins at about 550 astronomical units from the Sun, far beyond Pluto and well into the territory influenced by the inner Oort Cloud. Reaching this focal line is the challenge of millennia with current technology, but it is the ultimate prize. A single, modest-sized telescope placed precisely at that point, using the Sun itself as its primary lens, would achieve a magnification power beyond anything we can build. It could, in theory, resolve the surface features of an exoplanet orbiting a nearby star. We would not see a blurry dot but continents, weather patterns, and the lights of cities if they exist. The problem is stability and aiming. A telescope at a fixed point 550 astronomical units out would only be perfectly aligned with one specific patch of sky directly behind our Sun. To look at another target, you would need to move the entire observatory. This is where the Hills Cloud shifts from a passive backdrop to an active asset. Instead of a single, impossibly distant outpost, we could establish a network of them. Imagine a fleet of autonomous observatories stationed not at one fixed point, but on various stable orbits within the inner Oort Cloud. Each one occupies a different focal line for a different region of the galaxy. Collectively, they form a celestial surveillance network, a distributed eye with a resolution so sharp it could map entire alien solar systems in stunning detail. The cloud provides the necessary real estate and relative stability for such a permanent infrastructure. These stations would be self-sufficient, powered by compact nuclear reactors, their data transmitted back to the inner solar system via laser links. They would operate for centuries, patiently compiling the first true galactic atlas of worlds. This same principle extends to communication. The vast distances between stars make conversation agonizingly slow, with simple hello and goodbye taking years. A laser signal beamed directly from one star to another spreads out and weakens over light years. But if we use the Sun's gravitational lens as a focusing device, we can create a supremely powerful and narrow communication beam. A transmitter stationed in the Hills Cloud at the focal line could send a tightly collimated message to a similar receiver orbiting another star, where its own sun would focus the signal for collection. This turns each star system into a natural telecommunications hub. The Hills Cloud in this vision becomes the anchor for these relay stations, Its objects provide resources for construction and fuel, and its vast, stable orbits offer the perfect platforms for the precise alignment required. A network of such stations scattered through the cloud could form the backbone of an interstellar internet, a slow but steady web connecting humanity's future colonies around nearby stars. Data from probes exploring the Alpha Centauri system, or even broadcasts from an alien civilization, could be gathered, focused, and relayed with unmatched clarity. The silent, dark realm at the edge of our solar system, once thought to be the end of things, could become the grand central station for the next chapter of cosmic connection, its endless night pierced by the focused light of discovery and conversation. That silent network of relay stations would require more than just engineers and telescopes. It would need storytellers and artists. The sheer, overwhelming scale of the Hills cloud does not just inspire new technologies, it demands new ways of seeing. In the imagined art of a future that reaches this frontier, the dominant aesthetic is one of profound isolation and fragile beauty. Picture a painting not of a vibrant nebula, but of a lone human habitat clinging to the dark, tumbling surface of a captured interstellar asteroid. The only light comes from the weak, cold glow of its viewports, a tiny bubble of warmth against an infinite black. In the sky above, the Milky Way is not a faint band, but a crushing, brilliant river of stars so dense it casts faint shadows on the ice. The sun is there, but you have to search for it, a point of light no more significant than a dozen others, a reminder of home grown impossibly distant. This is the art of the edge, where the familiar cosmic landmarks vanish and humanity is left alone with the galaxy's immensity. Literature from this era would grapple with time itself. A novel might follow the crew of a generation ship not on a sprint between stars, but on a multi-century survey mission within the cloud, mapping its silent giants. Their drama would not be about explosive action, but about maintaining purpose and identity across generations when the destination is always just another dark, frozen world, and the journey is measured in lifetimes. These stories explore what happens to the human spirit when the concept of a neighborhood expands to a volume of space so large that light itself takes weeks to cross it. They ask if we can find meaning not in conquering a frontier, but in simply existing within it as caretakers of a cosmic archive. Cultural rituals would evolve around this new sense of place. The slow orbital periods of the cloud's captured worlds could become the basis for calendars, with years lasting centuries. The rare, close passage of another outpost's asteroid, a celestial event planned decades in advance, might be celebrated as a major festival, a brief window for physical contact in an otherwise digitally connected society. The very act of observing a long-period comet's arrival from the cloud's depths could be a sacred event, a live performance of cosmic mechanics that our ancestors on Earth could only reconstruct from ancient records. This art and culture humanizes the staggering science. It transforms the Hills cloud from a collection of orbital parameters and mass estimates into a setting for the next chapter of the human story. It answers the fundamental question of why we would even care about such a remote and inhospitable place. The drive is not merely for resources or safety, but for the same reason we have always painted the horizon and written about the sea, to find our own reflection in the vastness, and to declare through our creativity that even in the deepest cold and silence, we were here and we wondered. Supercomputers are now building a ghost of the solar system inside their memory banks. To understand a place we cannot see, we create its perfect digital twin, a virtual universe where we can run experiments that would take longer than the age of the cosmos. This is the realm of N-body simulations, a monumental computational effort to model the gravitational dance of countless objects over billions of years. The process begins with a simple but overwhelming question: what if we could rewind time? Astrophysicists program these simulations with our best theories of the solar system's birth, seeding a virtual protoplanetary disk with millions, sometimes billions, of digital particles representing those early icy planetesimals. They then set the laws of physics in motion and let the simulation run. The raw gravitational math is staggering because every single particle exerts a tiny pull on every other particle, a web of forces that grows impossibly complex with each added object. This is why only the world's most powerful supercomputers can handle the task, calculating trillions of interactions per second to see where all those virtual pieces end up after eons of simulated time. The goal is to see if the chaos of the early solar system, driven by the giant planets, naturally sculpts a distant spherical cloud that matches what we infer about the Hills cloud. Do the simulated exiled objects settle into that thick inner torus, or do they fly away entirely? The answer, written in lines of code and visualized as swirling galaxies of data points, has been a resounding yes. These digital twins robustly produce a dense inner reservoir, strongly validating Jack Hills's original mathematical prediction. They show us that our basic story of planetary formation is likely correct, and that the cloud is a natural, almost inevitable, consequence of our solar system's violent adolescence. These simulations do more than just recreate the past, they test our wildest ideas about the present. The most famous example is the hunt for Planet 9. When astronomers noticed the strange orbital alignment of Sedna and its kin, they turned to the digital twin. They ran the simulation again, but this time they added a new variable, a hypothetical planet with several times Earth's mass on a distant, eccentric orbit. They watched what happened over billions of simulated years. The result was striking. The gravitational influence of that digital planet shepherded the orbits of the scattered icy bodies, herding their closest approaches to the Sun into a cluster, just like we see in reality. Without the planet, the simulated objects remained randomly oriented. This doesn't prove Planet 9 exists, but it shows that such a world provides an elegant explanation for the observed oddities. It turns the hypothesis from a curious guess into a quantifiable, testable prediction. The simulation can even tell us where to look, generating a map of the most likely sky positions for the hidden giant based on how it sculpts its digital domain. This is science at its most powerful, using a synthetic universe to guide our exploration of the real one. The synergy driving this frontier is a fusion of astrophysics, big data, and artificial intelligence. A modern N-body simulation doesn't just produce a simple animation. It generates petabytes of data, a record of every particle's position, velocity, and interactions across cosmic time. Parsing this ocean of information for subtle patterns is a task perfectly suited for machine learning. AI algorithms can sift through the simulation outputs, identifying rare events like the capture of an interstellar object or pinpointing the specific stellar flybys that trigger the most intense comet showers. They can help refine the models, learning which initial conditions lead to a cloud that most closely resembles the one implied by our comet observations. This iterative process, where simulation data trains the AI and the AI improves the simulation, is creating increasingly precise and predictive digital twins. We are not just building a static model, we are cultivating a living, learning representation of the solar system's farthest frontier. It allows us to ask profound what-if questions with a few keystrokes. What if a star passed twice as close as we thought? What if there were 2 rogue planets in the cloud? What if the early solar system had 5 giant planets instead of 4? We run the simulation and watch the alternative history unfold in weeks, gaining insights that would otherwise be forever locked in the dark. This computational lens is our only way to explore the deep time dynamics of the Hills cloud, turning its silent, slow-motion ballet into a symphony of data we can finally hear and understand. But this digital twin raises a practical question with no easy answer: who owns the simulation and, more importantly, who owns the reality it models? As our gaze and ambition stretch to the Hills Cloud, we collide with a frontier not of physics but of law and ethics. The foundational document governing activities beyond Earth is the Outer Space Treaty of 1967, a product of the Cold War designed to prevent the weaponization of space and the claiming of celestial bodies by nations. Its core principles are noble. Space is the province of all humankind, not subject to national appropriation by claim of sovereignty, and it is to be used for peaceful purposes. But this treaty was written for the Moon and the planets, for places we could see and imagine reaching. It speaks in broad strokes, and its language grows hazy when applied to the incomprehensible scale and nature of the Oort Cloud. The treaty prohibits national appropriation, but what about corporate appropriation? If a private company sends a robotic harvester to a comet in the Hills Cloud and begins extracting water ice, does that constitute a claim of sovereignty, or is it simply using a resource like a ship fishing in international waters? The treaty says the exploration and use of space shall be carried out for the benefit and in the interests of all countries. But how do you ensure the benefits of mining a trillion-mile distant ice ball are shared equitably with all of humanity? The legal framework is utterly unprepared for an era where the most valuable real estate in the solar system might be a trillion chunks of dark ice in a volume of space larger than a star system. This ambiguity is a breeding ground for both conflict and innovation. Without clear rules, a first mover, whether a nation or a corporation, could establish de facto control over key resource-rich orbits or processing locations, setting precedents through action rather than agreement. The potential for a new kind of gold rush in the outer dark is real, and it demands we think now about the rules of the road before the first prospector sets out. Beyond the legal technicalities lies a deeper ethical quandary. The Hills Cloud is the most pristine museum we will ever have access to. Its objects are untouched time capsules from the solar system's birth. Every act of exploitation is also an act of destruction. Drilling into a primordial comet to extract water vaporizes ancient ices that have held their chemical secrets for 4.6 billion years. Moving a comet to a more convenient orbit for mining erases the gravitational history written in its path, a history that could tell us about the early migrations of the giant planets. We face a classic preservation versus progress dilemma, but on a cosmic scale. Do we have the right to alter this ancient environment before we have even begun to study it in detail? Is our need for fuel and water to expand into the galaxy a sufficient justification to dismantle the very archives that tell us how the galaxy formed? Some ethicists argue for a principle of cosmic preservation, designating certain classes of objects, like the first confirmed interstellar captives or the most chemically primitive comets, as protected scientific sanctuaries off limits to industry. Others propose a mitigation approach where mining operations are required to conduct exhaustive scientific surveys and preserve core samples in a solar system-wide vault before processing begins. This turns industrial harvesters into reluctant archaeologists, their drills collecting data as well as resources. The debate forces us to define what value we place on knowledge versus utility, and on the intrinsic worth of a natural wonder that no human eye may ever directly see. This leads to the most profound question of all: what is our role in this distant realm? Are we miners taking what we need from a dead landscape? Are we explorers documenting a frontier out of pure curiosity? Or are we stewards responsible for caring for this ancient heirloom on behalf of future generations of humans and perhaps other intelligences we have yet to meet? Stewardship implies a duty of care that extends beyond our immediate needs. It means planning for the long-term stability of the cloud itself, considering how massive extraction might alter its delicate dynamics and affect the natural comet delivery rate to the inner solar system over millennia. It means preventing the contamination of these pristine ices with Earth microbes, not just for scientific purity, but to preserve any potential native probiotic chemistry that might exist. And it absolutely means preventing conflict. The history of resource extraction on Earth is often a history of competition, inequality, and violence. If we allow that pattern to extend to the Hills Cloud, we risk projecting our oldest, darkest instincts onto the newest, darkest frontier. The alternative is to build cooperative frameworks from the start, perhaps through an international authority that licenses resource extraction in exchange for funding scientific exploration and ensuring a fair distribution of benefits. The cloud's vastness could, in theory, provide enough for everyone, but only if we have the wisdom to manage it not as a prize to be won, but as a commons to be shared. The silent, dark edge of our solar system is becoming a mirror, reflecting back at us not astronomical mysteries, but the fundamental questions about what kind of civilization we aspire to become as we step outward. Will we see only raw materials, or will we see a legacy to be understood and protected? The answers we forge in treaties and boardrooms today will echo for millennia in the space between the stars. This legal and ethical frontier is not the final boundary, but a launch pad. The Hills Cloud represents the last significant source of raw materials before the true emptiness of interstellar space. For a generation ship, a vessel carrying a self-sustaining human population on a centuries-long voyage to another star, this distant reservoir is the final supply depot. Such a ship would be constructed in the inner solar system, but it would be impossibly heavy if it had to carry all the fuel, water, and air for its entire journey from the start. Instead, it would embark on a slow, efficient trajectory toward the cloud. There, at the edge of our sun's light, it would rendezvous with pre-positioned resource harvesters. These robotic factories, fed by the ancient ice of captured comets, would top off the ship's massive tanks with water for fuel and life support, and load reserves of frozen gases and organic compounds for recycling and repair. The ship itself might even incorporate sections built from the refined metals of asteroid fragments also trapped in this gravitational eddy. After this last resupply, the colossal vessel would ignite its main engines, using the very water ice of the solar system's birth to push toward a new sun. The cloud transforms from a destination into a way station, the last bustling port of call in our home system. For swifter, lighter journeys, the cloud offers a different kind of boost. Picture a laser sail probe like the breakthrough Starshot concept, designed to reach another star in a human lifetime. Its strategy is to be pushed by a powerful ground-based laser. But that laser beam, even if perfectly focused, will eventually spread out and weaken over billions of miles. A relay station positioned within the Hills Cloud solves this. This station, powered by a compact nuclear reactor fueled by local ice, would house a second laser array. The tiny probe, having coasted for years on momentum from the Earth-based push, would sail into the cloud's realm. As it passed the station, the cloud-based laser would fire, giving the craft a second, powerful kick right at the solar system's exit door. This two-stage acceleration could dramatically increase the final speed, turning a 50-year journey into a 20-year sprint. The cloud's resources thus enable the infrastructure for the kick itself. Crossing the nominal boundary of the Hills Cloud would be a psychological milestone as profound as any physical achievement. For all of human history, every object we have ever observed, every world we have ever visited, has been held in the sun's gravitational embrace. Even the Voyager probes, now in interstellar space, are still technically within the diffuse outer reaches of the Oort Cloud's influence. But to pass beyond the denser inner cloud is to leave the last vestiges of our solar system's construction debris behind. The sun would no longer be the dominant gravitational force in your universe. Its light would be just another bright star, and its pull would be matched by the collective, gentle tide of the Milky Way. This is the moment you truly depart the harbor and enter the galactic ocean. It is a transition from being a resident of a solar system to being a citizen of the galaxy. This redefines the entire narrative of the Hills Cloud. We have spent this journey understanding it as a relic of the past, a threat, a resource, and a scientific archive. But in the longest view, it is none of those things. It is a preface. Its true purpose in the story of a spacefaring civilization is to be the staging ground. Its silent, frozen objects are the raw timber and fresh water stocked for the great ships being built on the shore. Its vast emptiness is the calm roadstead where those ships raise their sails. When we finally learn to live and work in that deep dark, we are not reaching the end of our journey. We are standing on the dock, looking out at the endless sea of stars and preparing to cast off. The cloud is not the edge of our world. It is the beginning of everything else. Buried within those frozen archives is a chronicle of our entire galactic neighborhood. The pristine surfaces of Hill's cloud objects are not blank slates. They are layered recorders, cosmic ice cores that have been silently collecting data for billions of years. Every particle of dust that has ever drifted through the solar system, every subtle shift in the sun's output, and every close encounter with another star has left its mark on these distant, untouched surfaces. Unlike asteroids in the inner system that are baked by sunlight and battered by collisions, these relics in the deep freeze have experienced almost no geological processing. Their surfaces are essentially unchanged since their exile, making them the most faithful historical documents in our solar system. The primary record they keep is of radiation. Over eons, the constant hail of cosmic rays, high-energy particles from across the galaxy, has bombarded their icy crusts. This radiation doesn't just pass through, it leaves a chemical fingerprint, altering molecules and creating unique isotopes right at the surface. By carefully analyzing the topmost layer of ice from such an object, scientists could reconstruct the history of cosmic ray intensity around our Sun. Was it stronger in the past, perhaps when our solar system was in a different spiral arm of the galaxy? This radiation record is intertwined with another, the history of stellar flybys. When another star passes close to our solar system, its gravity not only shakes comets loose, but its stellar wind, the stream of charged particles blowing from its surface, could also brush against objects in the Hill's cloud. This might deposit a faint layer of foreign material or create another subtle chemical signature in the ice. Finding and dating such layers in a cosmic ice core could let us build a timeline of our Sun's closest stellar encounters, turning theoretical models of past flybys into a verifiable geological record. Perhaps the most profound record is of the interstellar medium itself, the thin gas and dust that fills the space between stars. As our solar system orbits the galaxy, it moves through different regions, some denser with gas, others with particular types of interstellar dust grains. These particles would slowly, over millions of years, settle onto the surfaces of objects in the distant cloud. A carefully retrieved sample could thus contain a stratified collection of interstellar material, a layer cake of galactic dust from different epochs. We could analyze dust from when the Sun was in a stellar nursery and compare it to dust from when we were in a quieter region of space. It would be a direct sample of the galaxy's evolving composition, gathered not by a spacecraft sent between the stars, but by the patient billion-year accumulation of a frozen sentinel at the edge of our own system. To read this chronicle, we need to go and collect it. This demands a mission of almost unimaginable patience and precision, a robotic archaeologist on a multi-generational dig. One concept involves a spacecraft that doesn't aim for a single large object, but for the cloud itself. It would cruise into this vast region and deploy a collector, a vast, ultra-thin film like a spider's web, designed to capture the microscopic dust grains that pepper the space between the larger bodies. After years of collection, the film would be reeled in, sealed in a pristine canister, and the long journey home would begin, carrying back the accumulated dust of ages. A more ambitious mission would target a specific, sizable object, a Sedna-like world. After a voyage lasting decades, the spacecraft would enter orbit and deploy a lander equipped with a specialized drill. This wouldn't be a drill for mining, but for coring, like those used in Antarctica to extract ancient ice cores. It would need to gently extract a long, cylindrical sample from the surface down to a depth of several meters, preserving the delicate stratigraphy, the order of the layers. Each layer, from the modern surface dust down to the primordial ice at the bottom, would be a page in the solar system's diary. The core would be sealed in a cryogenic vault, kept at a fraction of a degree above absolute zero for the entire return trip to Earth, to prevent any melting or contamination that would scramble the historical record. The scientific payoff would rewrite textbooks. By comparing the radiation and dust records in the ice core with those from similar missions to comets in the inner solar system, we could distinguish between events that were local to our solar system and those that were galactic in scale. We could finally answer how often stars truly pass close by and what effect those encounters have on the planetary environment. We might even find, trapped in the ice, grains of stardust from specific types of stars that have since died, supernova whose explosions seeded the galaxy with heavy elements that eventually found their way into our planets and our bodies. These missions are not about finding life or immediate resources. They are about finding context. They seek to place our solar system's story within the grand narrative of the galaxy, to understand our home not as an isolated island, but as a traveler moving through a changing cosmic sea, with every change recorded in the silent, layered ice at the very edge of our light. The silent ice at the edge of our system may hold clues to the universe's greatest mystery. As we map the predicted structure of the Hills cloud and compare it to the odd orbits we actually see, a small but persistent discrepancy remains. The movements of Sedna and its kin are not perfectly explained by known planets or passing stars alone. This opens a door, however slightly, to a realm of profound speculation. Could the gravitational tugs we are trying to map be influenced not just by hidden planets, but by something far more exotic, something that permeates all of space yet remains utterly invisible? This is where our story brushes against the frontier of dark matter. We know dark matter exists because we can see its gravitational grip on galaxies, holding them together as they spin at speeds that should tear them apart. Yet for all its abundance, it has never been directly detected. It does not emit, absorb, or reflect light. It simply is a cosmic ghost that outweighs all normal matter 5 to 1. The prevailing theory is that it forms an immense, diffuse halo around our Milky Way, and by extension, a smoother, subtler halo around our own sun. Our entire solar system, from Mercury to the farthest Oort Cloud object, is swimming through this unseen sea. For most of the solar system, the effect is negligible. The gravity of the sun and planets is so strong it drowns out any whisper from dark matter. But in the Hills cloud, the rules change. Here, an object is so far from the sun that our star's gravitational hold is tenuous, a gentle leash. The forces at play are incredibly faint. In this realm of extreme delicacy, even the slightest additional influence could, in theory, leave a signature. Could the collective gravity of the dark matter halo, or interactions with individual dark matter particles, impart a tiny, cumulative nudge on these distant, loosely bound objects over billions of years? Some theoretical physicists have proposed models where certain types of dark matter, if they have specific properties, could create faint but measurable effects on the outer solar system. One idea suggests that if dark matter particles can interact with each other, they might clump together into diffuse streams or even form loose, extended disks within the galactic halo. If our solar system passed through a particularly dense patch or stream of this dark material, the extra gravitational pull could subtly warp the orbits of Hills cloud objects, herding them in ways that mimic the effect of a hidden planet. Another, even more speculative, idea involves not just gravity but direct collisions. Most dark matter models assume the particles pass right through normal matter like ghosts through walls. But what if, very rarely, they could interact with the nuclei of atoms in a comet's icy core? Over the eons, this would impart a tiny amount of heat or a minute push. For a comet in the warm inner solar system, this is irrelevant. But for an object in the deep freeze of the Hills cloud, where no other forces are acting upon it, this minuscule, constant pressure could, over billions of years, slowly alter its orbit in a detectable way. It is a fantastically small effect, like the gentle pressure of light from a distant star slowly pushing a solar sail, but accumulated across cosmic time. Now, it is crucial to state this plainly. This is fringe science. There is no evidence that dark matter is affecting the Oort cloud. The anomalies we see are far more likely explained by conventional, albeit unseen, masses like Planet 9, or by the gravitational echoes of ancient stellar encounters. Mainstream astrophysics rightly focuses on these more probable solutions, yet the speculative link remains intellectually tantalizing because it points to a revolutionary possibility. The Hills cloud could one day act as the largest and most sensitive dark matter detector ever conceived. Not a machine built in a lab, but a natural array of trillions of test particles already in place, whose positions and motions have been recorded by gravity over the age of the solar system. If we could ever achieve a detailed enough map of the cloud's structure and the precise orbits of its inhabitants, we might find patterns that no conventional gravity can explain. These patterns would be a signature of physics beyond the standard model, a faint fingerprint of the invisible universe left on the frozen archives at our solar system's edge. It is a long shot of cosmic proportions, but it reframes our entire quest. We are not just mapping comets to understand our past, we are calibrating a natural instrument that might, just might, sense the hidden fabric of reality itself. Living inside a comet is not science fiction, but a logical blueprint for survival in the deep dark. The primary construction material for a Hills cloud habitat is already there, surrounding you, ancient water ice as hard as granite in the perpetual cold. Engineers envision habitats not as free-floating stations, but as structures carved directly into the frozen nucleus of a captured object. Tunnels would be melted or drilled into the ice, creating pressurized living quarters, laboratories, and manufacturing bays. The ice itself, meters thick, becomes a perfect shield, blocking the cosmic radiation that permeates interstellar space. This isn't just shelter, it is integration, turning the local environment from a hostile void into a protective cocoon and a direct resource line. Robotic moles would constantly mine the surrounding ice, piping it directly into processing plants within the habitat. Some would be purified for drinking, bathing, and hydroponic agriculture. The majority would be cracked into hydrogen and oxygen, providing both breathable air and the chemical rocket fuel needed for local transport and station keeping. The waste heat from these industrial processes, carefully managed, would help maintain a livable temperature inside the ice caverns, creating a fragile, self-reinforcing loop of survival. Powering this isolated outpost is the fundamental challenge. Solar panels are useless where the sun is a mere pinpoint. The only viable, long-term solution is nuclear. We are not talking about the small radioisotope thermoelectric generators used on planetary rovers, but compact, sealed fission reactors, perhaps the size of a small car, buried deep within the ice shield for safety. These reactors could run for decades on a single load of fuel, providing the steady kilowatts needed for life support, industry, and scientific instruments. An even more speculative idea involves beamed energy from the inner solar system. An array of gigantic solar-powered lasers, stationed perhaps at the Earth-Sun Lagrange points, could focus a continuous microwave or laser beam precisely on a receiving station in the Hills cloud. This would require astonishing aiming precision over trillions of miles, and the beam would still spread and weaken, but it could provide a trickle of supplemental power, a tangible, energy-based lifeline back to the warmth of the inner system. The station would likely use both a robust nuclear heart with a beamed energy supplement, ensuring that a single point of failure does not mean a death sentence in the eternal night. The true test, however, is not engineering but the human mind. Communication with Earth would have a minimum delay of weeks each way. A simple question and answer would take over a month. This severs the possibility of real-time conversation, of mission control guidance, of hearing a loved one's voice in anything but a recorded message from the distant past. Crews would need to be utterly autonomous, making critical decisions about repairs, health, and safety without any input from home. The psychology of this isolation is profound. You are not just far from home, you are disconnected from the entire human timeline, living in a bubble of now that is weeks out of sync with everyone you've ever known. To cope, habitats would need to be designed as holistic environments. Virtual reality could simulate earthly landscapes, not just for recreation, but for mental health, offering a sensory escape from the endless black outside the ice walls. Artificial circadian rhythms would be meticulously maintained with interior lighting, as there is no sunrise or sunset. Social structures would evolve, perhaps toward small, highly interdependent clan-like units where every member's well-being is critical to the group's survival. They would develop their own culture, their own holidays based on orbital milestones or the arrival of a data packet from home, their own art born from the textures of ice and the patterns of the fixed, brilliant galaxy overhead. This is the ultimate off-grid experience, a society that must produce its own food, recycle its every molecule of air and water, generate its own power, and manufacture its own spare parts, all while conducting science on the very archive it inhabits. They are not just explorers, they are gardeners tending a single, fragile bubble of life in the most distant and silent garden imaginable, where the soil is primordial ice and the sky is a sea of stars that never twinkle because there is no atmosphere to make them shimmer. Their existence is a testament to resilience, a declaration that consciousness can not only reach the edge, but learn to make a home there, listening to the slow heartbeat of the galaxy from within a shell of ancient ice. That final leap from the dock would change us forever, confirming the reality of the Oort Cloud not as a theory but as a place we have touched, would trigger a philosophical earthquake in human consciousness. We talk about the overview effect, the profound shift astronauts experience when seeing Earth as a fragile blue marble against the black void. Now amplify that 1,000-fold. From the vantage point of a habitat embedded in a comet at the solar system's true edge, the entire magnificent structure we call home would shrink into a single, comprehensible whole. You would not see planets as separate dots. You would perceive the solar system as an integrated mechanism, a beautiful, layered clockwork. The sun is the brilliant central pivot. The rocky inner planets are a tight, quick-ticking inner gear. The gas giants form a slower, grander outer ring, and all of it is encased within the faint, spherical haze of the cloud you now call your backyard. This is the ultimate perspective. It collapses the vast distances that have always defined our loneliness into a single estate. We are not inhabitants of a planet, but custodians of an entire system, a connected biome of worlds, asteroids, and ancient ice, all bound by the same gravity and the same history. The concept of home expands irrevocably to encompass everything from the fiery heart of the sun to the frozen archives at its gravitational fringe. This new home has a stark, physical border. The Oort Cloud is that border. It is the shoreline where the familiar gravitational tides of our sun finally give way to the open galactic sea. Standing there, you inhabit the literal edge of the familiar. On one side, everything you have ever known, every story, every civilization, every loved one, exists within that faint, nested haze of light. On the other side stretches the true alien, the interstellar medium, where the rules are set by the galaxy at large, and the next anchor point is another star, years of travel away even at the speed of light. This forces a brutal and beautiful redefinition of territory. For all of history, humans have fought over lines on maps, borders of nations and continents. From the cloud, those lines are invisible, meaningless. The only border that matters is the one you are standing on, the cliff face between a single star's influence and the infinite. It makes the very idea of territorial conflict within our solar system seem absurd. A family squabbling in one room of a mansion while ignoring the dust gathering in the halls and the unlocked door to the wilderness outside. Our community, by necessity, becomes every human being back in that tiny haze of light, because out here there is no them. There is only us, a fragile thread of consciousness looking back at the entirety of its cradle. This vantage point dissolves old fears and presents a new, humbling responsibility. The existential dread of being alone in the universe meets its counterpoint. We are not adrift on a solitary speck. We are the organized, vibrant activity within a vast and intricate celestial habitat. The cloud is not empty space. It is the protected perimeter, the storage cellar, the historical record, and the launch pad of that habitat. Our role shifts from conquerors of a planet to stewards of a system. The questions we ask change. We stop asking how we can claim this or that asteroid and start asking how we maintain the health of the entire system. How do we preserve the pristine cloud archive while carefully using its resources? How do we ensure the gravitational dynamics that protect the inner worlds remain stable for eons? Our purpose becomes curation on a cosmic scale, tending to a garden whose seasons last for millennia. It suggests a maturity we have yet to achieve, where our measure of progress is not short-term gain, but the long-term sustainability and understanding of our entire stellar home. From the fringe, we see the masterpiece in full, and that view could finally compel us to grow into the wise, unified custodians such a magnificent home deserves. The Hills Cloud is the final great frontier within our own solar system. It is not a destination in the traditional sense, but a profound transition zone, a realm of immense scientific value, staggering potential resources, and deep philosophical weight. We have journeyed from its theoretical prediction to the icy messengers it sends our way, from the hunt for hidden worlds within it to the dreams of using it as a springboard to the stars. This distant, dark shell is far more than a collection of frozen relics. It is the ultimate context for our home. It holds the untouched records of our solar system's violent birth, acting as a 4.6 billion-year-old archive waiting to be read. It offers the material foundation for a solar system-wide civilization, its water and volatiles serving as the fuel and breath for future exploration. And it stands as a constant reminder of our connection to the wider galaxy, a gravitational shoreline where the influence of our sun begins to fade into the cosmic ocean. This makes the Hills Cloud a bridge in every sense. It is a physical bridge between the planetary realm we know and the interstellar void we yearn to cross, offering the last supplies before the long voyage. It is a temporal bridge connecting the chaos of our origins directly to the present day through the comets it dispatches. And it is a conceptual bridge, forcing us to evolve from thinking of ourselves as citizens of a planet to becoming stewards of an entire stellar system, with all the responsibility that entails. To understand this cloud is to finally see the full picture of our celestial address, from the fiery heart of the sun to the frozen, silent vault at its outermost edge. Our exploration of this frontier has only just begun in the mind. Turning that understanding into reality will require generations of patience, ingenuity, and international cooperation. It will demand telescopes of unprecedented sensitivity, spacecraft of legendary endurance, and a societal commitment to discoveries whose fruits we may not live to see. This is the next giant leap, not to another world, but to the very framework that contains all of them. It begins with supporting the science that maps the darkness, from planetary astronomy to deep space mission design. It continues with fostering the curiosity that looks past the bright, familiar planets to wonder about the shadows at the edge of the map. So, as we conclude this look into the deep dark, the question turns to you. Which aspect of this hidden frontier captures your imagination the most? Is it the ancient, pristine ice holding secrets from the dawn of our world? Is it the potential for hidden giants like Planet 9 still lurking unseen? Or is it the vision of this silent cloud one day humming with activity as the dockyard for humanity's journey to the stars? Share your thoughts below, and let's keep looking up and looking out to the next frontier waiting